Hey guys, today we're going to be starting a new unit. It's our last unit for the year and it covers energy. So today we're going to be learning about the different types of energy, and then you're going to be doing an exploration using a simulation on your phone or a laptop, whatever you've got to work with. So make sure you've got a notes packet from the front, and we're going to be starting on page 1. So we've got 3 big concepts we're going to go over today. The first one is energy. You do have to know the definition for energy. It is up here. It says energy is defined as the ability to do work or produce heat. So doing work is basically getting objects moving, and producing heat is also getting objects moving, but on a molecular level. So when we produce heat, the heat is molecules moving quickly inside an object, so it's still making things move. And there's different types of energy, and they're all measured in the unit joules, which we represent as a capital J. So the big forms that we're looking at here, and there are others and like subcategories of these, but there's 4 big ones that we're looking at. The first one is mechanical energy. So mechanical energy has 2 different types within it, 2 subcategories, kinetic and potential. If you've taken physics or IPC, I'm sure you've heard these. Kinetic energy is the energy of motion. So when an object itself is moving, that's called kinetic energy. Now, the other form of mechanical energy is called potential energy, which is the energy of position. An example of potential energy is gravitational energy. When you hold an object high above the earth, it has energy based on its position. When it's held high, it has the potential to move a lot. So we call it potential energy from position. Other types of energy include thermal energy, which is the internal energy of an object from heat. So that's all of its molecules moving around inside of it. We've also got chemical energy, which is stored in chemical bonds, like the ionic and covalent bonds that we learned about way back in the day when we studied compounds. And another type is radiant energy, which is the energy that's stored in electromagnetic waves, which is all types of light. And that covers the entire light spectrum, going from the radio low energy end to the gamma high energy end. All light includes energy, and it's called radiant. So those are just some of the forms of energy. There are other forms that we're not going to talk about. There's tons of different things there. But these are the main ones we're going to be discussing in this unit. Our next topic is about systems. So when we're studying energy, we need to consider our system. And what that means is the set of things that you are studying. So the set of things that you care about in any given situation is called the system. It is a set of things. And then everything that isn't a part of your system that you don't care about is called the surroundings. So every time you're considering energy, you need to figure out what objects are in your system and what is left over to be your surroundings. If there is energy transfer between the two, so you got a certain system that you've set, and it does transfer energy to its surroundings, that's called an open system. Like the door is open for the energy to go through. And the opposite of that is a system that doesn't transfer energy with its surroundings. It's called a closed system. Now, technically in the universe, there are no closed systems. The universe as a whole is always transferring energy with everything else in the universe. So everything is an open system. But when we're studying science, we like to simplify things down by not considering those things that are negligible. So, for example, we on the Earth are experiencing a gravitational pull from Pluto because due to the nature of gravity, everything that is massive pulls on literally everything else. But it's so far away that it doesn't really matter, so we don't consider it. Even though it's technically there, we don't think of it as part of our system because it doesn't really matter in the scenario we're looking at. So even though there aren't really any closed systems in the universe, a lot of times in science we will consider a system closed because that's a good enough approximation to get the results that we need. So for an example, we're going to look at this picture down here of a Bunsen burner under a test tube. And we're going to identify the system and the surroundings. So if we were conducting an experiment and we needed to heat a test tube up or heat the contents of a test tube up, really the only heat transfer we care about is the flame and the stuff that's inside the test tube. So the stuff we care about is called the system. The system here would include the burner, which is giving off the energy, and the contents of the test tube, which is receiving the energy. And usually when you hold something over a flame like that, you're just trying to heat up whatever's inside your container. So our system that we care about is the burner and the contents of the test tube. But there's other stuff that's around there that's also feeling the heat. And those things are called the surroundings because they are there, but we aren't considering them. We don't care about them very much. So some things that are in our surroundings are like the test tube. It's holding our liquid, but we don't care if the test tube is heating up or not. There's also the test tube holder. There's the hand. And since this is probably on Earth rather than in space, there's also going to be some air surrounding all of these things. So our system, the stuff that we care about, would be the burner, and the stuff that's inside the test tube. The surroundings is everything else. And we're also tasked here with labeling the energy types within the system. So some energy types here include, we've got thermal energy that's happening. It's going from the flame and we're heating up the contents of the test tube. So there's thermal in both places. You've also got radiant because flames give off light. And you probably have some chemical energy inside your chemical. And you could also construe this to be potential energy because we are holding the test tube up over the ground, so it has the potential to fall and speed up. So it does have some potential energy. So we got lots of different types of energy there. All right, let's go ahead and flip on over to the next page and look at the conservation of energy. We've done conservation of mass before, and back in the day when we did conservation of mass, conservation meant something stays the same. Conservation means stays the same. So when we did conservation of mass, what we said was that the total mass before a reaction has to be the total mass after a reaction. And that's what we're looking at here again with conservation of energy. Conservation of energy is saying that total energy is always going to be the same. Total energy before is equal to total energy afterwards. Another way of saying this is saying that energy cannot be created or destroyed. And you've probably heard that before. So when we are working with energy and it goes missing from one place, it can't have been destroyed. The law of conservation of energy says we can't destroy it. So what happens is that instead it is transferred somewhere else. It's going to be transferred from object to object, or it can also be transformed from one type of energy to another. So, for example, if you take your wonderful hot cup of cocoa or coffee or tea outside in the winter, or even if you just leave it sitting on a table for a long time in your house, it ends up getting cold. So it started off with a bunch of thermal energy, but after a while, that energy seems to be gone. And the question is, well, was it really destroyed? No, it was not. It was just transferred to the air around it. And then the air spread it out. And so the air heats up a little bit, but your coffee gets pretty cold. And it can also be transformed from one type to another. For example, when you, standing still, decides to start walking or to sprint, you, as a person standing still, didn't have any kinetic energy, but when you start walking, you do. That kinetic energy isn't being created, it's being transformed from the chemical energy found within your body. So your body takes food, which stores chemical energy, and it releases that energy, allowing you to change it to kinetic. So you're not actually creating the energy, you're just transforming it from chemical to kinetic. And this law is true almost everywhere. So our sentence here is every process, including chemical reactions, has to follow the law of conservation of energy. And I like to tell students when I'm lying to them, conservation of energy is true almost all of the time. It is not true during fission and fusion reactions or with antimatter, because those actually follow the law of conservation of mass energy, which was Einstein's famous equation E equals mc squared, and it's stuff that happens on the peripheral of daily life. You don't see it anywhere in your daily life. So we're not really going to go into that, but I do like to tell you when I'm telling you something that's not entirely true. Conservation of energy is not technically always true, but for the most part, it is. So we're going to be considering it a law in this class. If you want to know more about why it's not really true, ask me when I get back. I'd love to talk to you about it. Well, here in the next sentence, we have the scenario I already recounted for you. Your coffee cup out in the cold. And the deal with that is that the coffee is losing some energy, but the air around it is gaining the energy. So our sentence down here with the blanks says energy that is lost in one place is gained in another. So when you have energy leaving somewhere, it has to be going somewhere else. It's not just being destroyed. If you have energy coming in somewhere, it has to be coming from somewhere else. It's not just created. That's the law of conservation of energy. So your assignment today is a virtual lab. You can do it on your phone or on a laptop or on a tablet, whatever you've got. If you don't have any of those things, you're welcome to congregate at the smartboard and do it up there. But it's going to be based on a FET simulation. To get to the FET simulation, you can either go to Google Classroom and click on the link, or you can scan this lovely QR code and it will take you straight to the FET simulation, which I will pull up here. All right, so once you get to the FET, you'll come to this screen. It says Energy Forms and Changes, and you'll have two options, Intro and Systems. We're going to start with the Intro. We'll get to the Systems eventually. So you'll click on the Intro. My lovely one is being kind of slow. Anyway, so you'll have a display that looks like this. You'll follow the instructions exactly as they are on your sheet. You'll be heating some things up, cooling them down. But in order to know what's going on and see what you're doing, you have to click over here in the upper right-hand corner. There's the energy symbols checkbox. So that one's going to need to stay checked all the time. It allows you to see the energy as little e's. So if something is gaining e's, it's gaining energy. If something's losing e's, it's losing energy. And you can see like my brick heating up there then gives off energy to its surroundings, which is the air. So you can heat them up and cool them down. Sometimes you'll have to link your two buckets of fire together. So that's that button that says link heaters, and it'll make them either both heat up and cool down, or vice versa. You can take your objects, put them into the liquids, see what happens, heat up your liquids, whatever you need to do according to the instructions. You're also welcome to play around with it, see how it works, all that fun stuff. So follow the instructions for that one. After you've done the intro, you'll get over to the systems, which you get to by clicking down here at the bottom. You'll get a kid on a bicycle running a generator with some water. Again, you need to click the energy symbols button in order to see the energy flowing. So at first it's just a person on a bicycle. There's energy in their stomach, which is where your food is. It's changing to energy over here. Making the generator go, which is eventually going to make the water heat up. Now, as the energy is going through, you'll see the color is changing. And if you look over here, also, y'all know me, I'm a Star Wars nerd. They have lightsaber pointers on this program, so that's pretty great. Anyway, over here with the forms of energy, you can see color-coded what type of energy is what. And once our chica over here runs out of food or chemical energy, you have to click feed me in order to get her to go again. So you can run the simulation as is, answer questions, but you'll also be able to create your own system, which lets you switch out the components here. So like, for example, here we've got the sun giving off some radiant energy. We can add in some clouds if we want, do whatever we would like. In the middle here, you can have a generator or some solar power. And then over on the end, you can power all sorts of different things. So your system that you make in the end is up to you. And all of the directions should be right on your lab sheet. Good to go. So again, you can do this on your phone. You can also do it on a laptop or on a tablet or the front computer. But it does need to get done and turned in today. If you have questions, this video will be available in Google Classroom on the classroom assignment, so you can refer back and watch it on your own if you'd prefer. Up to you. All right, get cracking. I expect to see all of these when I get back this afternoon, and we'll move on to exothermic and endothermic reactions tomorrow. Hope y'all are having a great day. See you tomorrow.